Welcome to the hands-on workshop, Performance Optimization for Intel Xeon Phi Processors. This is episode 3. I am Andrei Vladimirov with Colfax International. In this episode, I will talk about vector instruction support in Intel Xeon Phi processors. Vector instructions are one of the implementations of SIMD parallelism. SIMD stands for Single Instruction Multiple Data. Intel Xeon Phi processors support vector instructions. This means that they can apply a single stream of instructions to multiple data elements at once. To understand how it works, it is easier to start by understanding what happens in a scalar, non-vectorized application. Suppose I'm adding two arrays, element by element, and these arrays contain integer or floating point numbers. For every pair of numbers, I will have to issue an addition instruction, which will have a certain latency associated with it. To add two arrays together, I will end up issuing as many addition instructions as I have elements. In contrast, if I have a program that uses vector instructions, then I can issue one addition instruction for several numbers at once. And the idea is that thanks to specialized vector processing units in my architecture, the latency of this vector addition is going to be the same as the latency of just one scalar instruction. So potentially I get a speed up equal to the width of my vector register. How many numbers I can fit into a vector register is determined by the instruction set supported by my CPU and by the data type with which I am working. In Xeon Phi processors, the instruction set supports 512-bit vector registers. If I'm dealing with single precision arithmetics, my numbers are 32-bit long, and it means that I can fit 16 numbers into a vector register. In double precision, my numbers are 64-bit long, and I can potentially fit 8 numbers into a vector register. And these values are the potential speed up thanks to vectorization in single precision and double precision due to vectorization. Because there are two vector processing units in each core of Xeon Phi processors, as we discussed in episode 2, I need to have a stream of vector instructions in my code so that the core can schedule my instructions on to the two available VPUs. The instruction set supported by Intel Xeon Phi processors is AVX512, and this determines the type of operations that I can run with vectors. AVX512 is a brand new instruction set introduced with Xeon Phi, and it is structured into modules, of which 4 are supported in Intel Xeon Phi processors, and some others will be added for future Xeon. I will talk about these 4 modules in a minute. In addition to the new instruction set, Knights Landing processors have legacy support for older instructions used by Xeons. For example, AVX and SSE instructions can be run out of box on Knights Landing. This means that if I take an executable that is compiled for an existing Xeon processor, I can run this executable on Knights Landing without any recompilation. Of course, it will not achieve the optimal performance, but at least it will run out of box. So AVX512 is the instruction set that you want to use for maximum performance. But you can also count on KNL being able to run legacy instructions such as AVX and SSE for compatibility reasons. The 4 modules supported by Knights Landing processor are AVX512F, CD, ER, and PF. F stands for fundamentals. And this is the subset of instructions where you find the basic loading and storing instructions and essential arithmetics such as plus, minus, multiply, divide, fuse, multiply, add, and type conversions. Largely, AVX512F is the extension of most Xeon instructions such as AVX2 and its predecessors from 256-bit to 512-bit vector registers. Conflict detection is a set of instructions useful for binning, and I will demonstrate it in episode 7. Briefly, this instruction set is good news for Monte Carlo calculations. AVX512ER contains exponential and reciprocal calculation for computing the exponential function, the reciprocal function, and the reciprocal square root function with vectors in single precision and in double precision with high accuracy. And finally, AVX512PF is prefetch instructions for gather and scatter operations. You can learn more about using these 4 modules in our Coolfax research publication at this URL. The reason that AVX512 is broken into several modules is that these modules are going to be reused selectively in future Xeons. For instance, AVX512F and CD are going to be used in future Xeons based on the Skylake architecture. To make your code use vector instructions, you have two approaches, a choice of 2 approaches. You can do automatic vectorization or explicit vectorization. With automatic vectorization, you will express your code with scalar instructions using loops, CMD-enabled functions, and array notation. A vectorizing compiler can understand which loops have opportunities for data parallelism, and a vectorizing compiler will implement vector instructions in your calculations. So for a loop, it will take the loop iteration space, split it up into chunks of 8 or 16 iterations depending on your data set and data type, instruction set and data type. And each of these block of iterations are going to be executed with 1 vector instruction in multiple vector lanes. This is a good portable approach. If you want to compile your code for an older processor or for a newer processor, all you have to do is change a compiler argument, and you will get the new instruction set in your executable. In addition, it is possible to tune the behavior of the compiler with directives to help the compiler better vectorize your code and get more efficiency. Situation is very different with explicit vectorization. With explicit vectorization, you will split up your loop into blocks manually, and for each block of numbers you will have to load data from memory, then you will do vector arithmetics, and you will store the result back in memory. For your operations, you will be using special data types which have the meaning of a vector register. In this case, M512D means a vector 512-bit long of packed double precision numbers. As you can see, you have full control over the instructions that you want to run, but portability is limited. If you want to run this code on an older processor, it may simply not run if these instructions are not available. If you want to run the code compiled from the same application compiled from the same source code on a future processor, it may run, but only in legacy mode. A good vectorizing compiler, such as Intel C, C++, and Fortran compiler, is very powerful in terms of vectorization, and it has some additional wisdom about the procedures that it uses for vectorizing code that is not available simply from reading the instruction set specification. So we advocate automatic vectorization in all our trainings. And we demonstrate how to write code in such a way that indeed vectorization opportunities are picked up by the compiler, and that vectorization is efficient and portable. With Intel compilers, you can produce code for Knights Landing as long as your compiler version is 15 or newer. To tell the compiler that you wish to produce code for Knights Landing, you can use the -x flag followed by the instruction set code. XMike AVX512 will compile for Knights Landing, so it will use the 4 modules AVX512F, CD, ER, and PF. If you want to compile for future Xeons, you can use Core AVX512, and if you want to produce code that will be guaranteed to run both on Xeon Phi and on a future Xeon, then use Common AVX512, which will only enable fundamentals and conflict detection. If you want to compile your code with GCC, the GNU compiler suite, you can do it starting from version 4.9.1, which supports AVX512. And again, you will express vectorization opportunities with loops. To enable automatic vectorization, you can use O3, and then you will have to list explicitly the modules of AVX512 that you wish to use in compilation. To convince yourself that you are indeed using vector instructions, one of the ways is to compile the code with argument -s, which will produce assembly instead of the executable. And then this assembly listing, you can view it, and when you find your vector instructions, make sure that they are operating on ZMM registers. These are the registers used in the AVX512 instruction set. In general, this is not an easy task to take an application that doesn't use vectorization and to vectorize it. First of all, you have to express vectorization opportunities to the compiler, and you have to do it in such a way that there is enough parallelism to utilize both multiple cores and vector instruction support. To make your vector instructions efficient, you probably will have to do some loop transformations to make sure that memory access is not interfering with your arithmetic performance. And finally, you may need to change the data containers that you are using for example, achieving unit stride and otherwise improving vectorization patterns. We talk about these techniques in detail in our How series, and there is a link to this comprehensive training in episode 10 of this workshop. Fortunately, there are tools that can help you with the process of vectorizing your application, and one such tool is Intel Advisor XE. We have a paper on Colfax Research where we demonstrate a case study where step by step we take an application with poor vectorization and improve it. You can download it at Colfax Research. At the same time, all of this complexity is not specific to Knights Landing. In fact, these procedures are going to be required for any vectorizing processor, including a Xeon and including non-Intel processors. Therefore, the work that you invest into modernizing your code and into making it take advantage of data parallelism is going to pay off on a large array of platforms. Knights Landing is one of them. In the next episode of this workshop, I will talk about memory organization in Knights Landing processors, focusing on the usage of their high bandwidth on-package memory.